Hello everyone, let us start today's session. So, welcome to the week 6 problem solving session for deep learning course. I am Tanuka from ISC. So, today we will be discussing some problems about backpropagation gradients and some problems on PCA, autoencoder and related things. So, can anyone confirm if my screen is visible to you?
Yes, ma'am, visible.
Okay, thanks. So, let us start with the first problem for today. So, this is basically the node based approach for back propagation. So, the question says, suppose a neural network has 3 input nodes A, B, C. There are 2 neurons X and Y. So, X is A plus B and Y is X into C. Then what is the gradient of y with respect to ABC? So, you have 3 input nodes. We have 3 input nodes A, B and C. Now, our first neuron is X, which is A plus B. So, we are doing plus operation between these two. This is our X and our Y is X times C. So, this and this are getting multiplied, that is our Y. Now, you have to find the gradient of Y with respect to all these 3 inputs. So, how do you do that? So, here you have X equal to Y equal to X into C, right? And your X is again A plus B into C. So, simply in this case we can simplify the expression for y and take it in terms of A, B and C, and then it is simple. You can simply take the gradient of y with respect to A, with respect to B and with respect to C. Also some values of A, B and C are given. So, putting those values you can finally find the numeric value of the gradients. So, if you compute, let us say, gradient of y with respect to A dy dA, if you take the derivative of this expression with respect to A, you get C, and here it is given that C is minus 4. So, your dy dA is minus 4, that is gradient of y with respect to A, that is minus 4. Similarly, if you do dy dB, that is also C, which is minus 4, and if you do dy dC, that will be A plus B. So, your A is 6 and B is minus 1. So, 6 minus 1, 5. So, these are the 3 gradient values. So, gradient of y with respect to A, B and C, and at those given values of A, B, C as given here, these gradients are minus 4 and 5. So, this is a simple example. This is kind of, you have a computational graph here and you are simplifying to get the expression of the final output in terms of the initial input nodes. And once you have that, you can simply take the derivative, put the values of the inputs and you can get the final expression for all the gradients. So, this was a simple expression. Now, let us see this one. Let us say y equal to max of AB and it is given that A is greater than B. Then what is the value of dy dA and dy dB? So, your y is max of AB and here it has been provided that A is greater than B. So, your y simply becomes A because A is greater than B and you are taking max of AB. Now, this is again a simple expression. If you do dy dA, it becomes 1, and if you do dy dB, it becomes 0. So, this is how you do for the maximum operation. So, if one of your node is taking the maximum of 2 inputs, in that case the gradient will pass based on this type of a rule. So, there is one type of unit in case of neural network which takes this maximum, which is called the max pooling layer. So, in this problem we will try to see that. So, during back propagation through max pooling with stride, the gradients are what? So, in this case, let us take the example that max pooling you can take on different window sizes or over different number of inputs. You can take the max pooling and you can shift the max pooling window by the stride value, and you can again take the maximum. Here let us say you have two inputs. You have two inputs, let us say x and y, and you are taking the maximum of that for doing the max pooling. So, your output will be simply, let us say we write it f, which is max of a comma b.
Madam, stride means what, madam?
So, stride means the shift. So, when you do this max pooling operation, let us say the input you have is array which has these values. Let us say 1, 2, 3, 4, 5, 6, 7, 8, 8 values are there in the array. Over this you want to do the max pooling, let us say, and you want to do the max pooling over say 2 elements. Your max pooling window size is 2. So, first you take the maximum of these two values. Now, you take the maximum of these two values. So, you are shifting the window by one element. So, in this case your stride is 1. But if you let us say take first these two window, then you take this two window, then your stride is 2. So, it is basically the number of indexes by which you are shifting your max pooling window to get all the max values. That is what stride means. Basically, in case of overlapping window, the window shift is the stride. Is that clear to you?
Yes, madam. Yes, madam. Okay.
Okay. So, now we took the simplest operation. We just took the, let us say, first two elements, and you are taking the maximum of that, and this is the final your output. Now, let us say you have some target value that you have to achieve at this point, and you are computing some loss measure, and you are getting the loss as L. So, during back propagation, basically this loss is what you back propagate through your network, and you compute the local loss at each nodes. So, here let us say your loss at this output is L. So, now you have to take the, you have to know the contribution, or you have to back propagate this L to earlier nodes. So, you will have to compute del L del x and del L del y. So, by changing x and y, small change in x and y, how that impacts the loss at the output L. So, that you need to compute, that is del L del x and del L del y. Now, x is not directly related to L, right. So, x gives rise to f. F is the predicted value, you can say, and you are comparing that with your target value to get the loss. So, basically your loss is a function of this f, and this again is a function of this x. Sorry, I have written here a and b, this should be x and y. So, when you back propagate the error, if you want to compute, let us say first del L del x we want to compute. So, del L del x will basically be del L del f into del f del x. Similarly, del L del y will be del L del f into del f del x. Now, we do not know the loss, particular loss measure in this case. So, let us say that is some function g. So, we are assuming that del L del f is some function g. So, if that is the case, then this becomes g into del f del x, and this becomes, g into del f del y. So, now we have to compute del f del x and del f del y. So, this is again basically taking the gradient of the maximum function as we tried in the last problem. but here you have to consider more cases. In the last problem it was given that A is greater than B, but here no such restriction is there, any possible combination can be there. So, our f is max of x y. So, first let us say we take the condition x is greater than y. If x is greater than y, then your f is equal to x. So, your del f del x is 1 and del f del y will be 0. And when you have x less than y, let us say, then your f value becomes y, because now y is the maximum. So, your del f del x now becomes 0 and del f del y now becomes 1. So, if you take our expression here, so the final expression for del L del x that we need, that is g into del f del x. So, your del L del x is basically g into del f del x. Now, del f del x is 1 if x greater than y and it is 0 if x less than y. So, if you put that value, so this will be g into 1, that is g if x greater than y, and it will be 0 g into 0, which is 0 if x is less than y. Similarly, for y also we can compute. So, our del L del y was g into del f del y. So, del L del y was g into del f del y. Similarly, we can put the values of del f del y for the two conditions. So, we will get this is 0 when x greater than y and g when x is less than y. So, if you visualize it, so you have x and y here, two inputs, and you are taking the maximum over here, let us say, and you are getting f. Now, you are propagating the error loss contribution backwards. Now, in case your x is greater than y, so that among these x and y, x is the maximum 1. In that case, your del L del x becomes g and your del L del y becomes 0. This is when you have x greater than y. And if you have x less than y, in that case, your x is less than y, that is y is the higher one. In that case, your del L del x becomes 0 and your del L del y becomes g. So, you see, among the two inputs, whichever is the higher one, you are having a non-zero gradient in that direction, non-zero contribution from the loss in that direction. In the other one, you are having a 0 gradient. So, if you see the options that were given, so during back propagation through max pooling with stride, the gradients are evenly distributed, sparse gradient are generated with non-zero gradient at the max response location, differentiated with respect to responses, none of the above. So, in this case you can see you have towards the maximum input you have a non-zero gradient, but the other one is 0. So, you are getting a sparse gradient. So, you have sparse gradient and your non-zero gradient is at the maximum response location. So, towards the maximum input. So, this is basically the case when you are doing max pooling and you want to back propagate your error through that max pooling layer. Then you get a sparse gradient for the loss with non-zero gradient at the max response location. I hope the derivation is clear to everyone. If you have any doubts, you can ask at any point. So, now we will move on to the next problem. So, this is also a similar one on these gradient based concepts. So, here you have three layers. First, this first layer and last layer are black boxes, these two. In between there is a layer which is performing e to the power x. So, here your input is 2, which is getting through e to the power x, and you are getting y, and your gradient is 2 here and g here. You have to compute g of this function. So, this 2, this is basically the gradient of the loss from all next layers. So, the contribution of the final loss at this point is 2. Now, you have to compute g, which is the contribution of the loss at this point. At this point you have to compute. So, at this point you know the gradient, at this point you have to compute the gradient. And what operation is happening here? Your y is e to the power x. So, if you take the gradient, that will be del y dy dx, let's say, that will be e to the power x. Now, here your input was 2. So, this block is performing e to the power x, that means if your input is basically the x, so that is 2. So, it is basically taking the exponent of 2. So, your output y in this case is basically e square, okay. And your derivative, that is dy dx, that is again e to the power x. So, that will also be e square. So, the gradient be due to this particular box, that is e square. Now, if you want to compute g, what we do is you have to take the gradient till this point, then multiply the gradient contribution from this block. So, this till this point your gradient was 2, along with that here your gradient contribution is e square. So, your final gradient at this point of the network, which is g, that is 2 e square. So, you basically keep on multiplying the gradients for the previous for the next layers to get to the previous layers. Since you know the gradient at this point is 2, so you simply take that and you take the gradient for this particular layer and multiply the 2. This is how you get the gradient at this point. Okay. So, these were some basic problems on how you do back propagation, some simple derivative function that is commonly needed for computation of the back propagation gradients. Now, we will move on to our next topic, which is PCA. So, if anyone has any questions from these derivative based problems, you can raise it at this point. I will wait for 2 minutes maybe. If any doubts you can ask at this point.
Ma'am,
Yeah.
the problem number 3, there we are considering two different conditions.
Yeah.
If x is greater than y and x is less than y.
Yeah. Right.
Correct. And when we are finding out delta of L with respect to x, then we are considering again two conditions.
Yeah. Yeah. Right.
Okay, that I could not understand. Why we are considering again, if we considered x is greater than y, then we are writing simply 0 for x is not greater than y. It is like that?
No, like when you are computing this derivative of this maximum function, the derivative value basically changes depending on this condition, right? If you have
Yes.
x greater than y, this is the derivative. X less than
Correct.
y, this is the derivative. Now, here when we are computing del x, you have to put the value of del f del x here. So, that value
Yes.
will be either 1 or 0 depending on this particular condition.
Yes.
So, when you are having this condition, you are putting the del f del x value as 1. When you are having this, you are putting the value as 0. So, two conditions are coming up there also, because that
Okay, understood. Understood. Thank you.
Okay, so let us move on to our next topic, which is PCA.
Madam, I have one doubt, madam.
Yeah.
Madam, now if there are two hidden layers,
Hmm.
if you want to find out the gradient of the back to this one more layer is there, then we have to twice differentiate this dy by dx.
Yeah, right. So for each layer you will have to do once.
Okay, madam. Every layer once we have to go on differentiating.
Huh. So basically when you have hidden layers, it will not again be just a linear function like this. It might be that you have a non-linearity on top of a linear combination. So you will have to take the gradient first with respect to the non-linearity, then respect to the linear combination for each layer. And if you do not have a non-linearity, then just the linear combination part, the xiwi summation part.
Okay, madam. It can be a combination of linear and non-linear functions also.
So the basic in deep neural network, when you have a neuron that basically performs this, right, wixi, and you have a non-linearity on top of that, which is sigmoid or some ReLU function, some non-linearity will be there. So when you take the derivative, you have to consider this first with respect to this non-linearity. You take the derivative, then you consider this thing.
Yes, madam. But autoencoder, in that autoencoder theory, whatever we studied, no, madam, it's a combination of it learns for nonlinear functions as well as the linear functions.
Yeah, right.
Yes,
So
madam.
basically, depending on what relation you want to learn, this f, this function will change. If you just want to learn a linear mapping, then this f can be just a linear function. Nothing, you just put a linear function in place of this, maybe just 1, f equal to 1 you put. But if you want to see a non-linear mapping, you will have some sigmoid or some ReLU or some other non-linear function in place of that, exponential maybe. So depending on what function you take, that you have to consider while taking the derivative also. So if you are taking linear, then there is no issues.
Madam, can you give me some real life example where such kind of nonlinear functions can be implemented? I mean, might be in image processing,
Yeah,
image classification or segmenting or compression.
in most of the places, when you have a very high let's say you have a classification problem where the two classes are not linearly separable. So for example, you have, let's say you have a set of data points within a circle which belongs to one class, and you have another set which is outside this circle. So you cannot, if you want to now find a, let's say this is not a auto encoder, but a simple deep neural network I am talking about. So this is a very simple example, you can think
Yeah,
similarly.
we cannot separate by a simple classification
Simple
problem.
classification, but you, if you do square, then it becomes a separable. So if you do take square function, simply the square points, cross points will come this side and this will come this side. So in that case, you will have to put a non-linearity in place of the in the neurons. So just linear combination can't serve your purpose in that
Yes.
case.
Madam, while calculating this non-linearity
Yeah.
loss function,
Loss function. Okay.
why do we take mean squared error, MSE?
We not always, we don't take mean square error. That is one type of loss function that we can consider. So when you are kind of having a, let's say, regression problem where you just want to make your output close to the target value, that's the aim, then we take this MSE. We can also take mean absolute error, that's also another, or we can take correlation coefficient also. We can try to maximize any of those. MSE is just a commonly used choice, that's it.
Okay, madam, thank you.
So let us now move on to the next question. So here we'll do some examples on PCA. So the first question we have is, consider you have 4 sample points and both all 4 of them are 2D real vectors. So basically this is one sample 4 1 2 3 5 4 1 0, 4 samples you have, each are 2 dimensional. Now you want to represent the data in 1D using PCA. So just want to do a dimensionality reduction from 2D to 1D using the PCA method. Compute the unit length principal component directions of x and then choose from the options below which one the PCA algorithm would choose if you request just one principal component. So first we have to compute the principal components according to the PCA algorithm. So the inputs that we have are these are the inputs. So in PCA what do? We first remove the mean from the data points and then we compute the covariance matrix. Once we have the covariance matrix, we compute the eigenvalues and eigenvectors. So the each eigenvector corresponds to one principal component and the eigenvector corresponding to the highest eigenvalue, that corresponds to the maximum variance direction in the data space. So first step that we have to do is we have to subtract the mean of these data points from each of the data points. So the mean, if I write it as x bar, that will be mean is 3 2. This is the mean. Now you have to compute the mean subtracted vector, which is, let us say, x bar. So this is basically x minus x bar, which is x prime, that you need to compute. So what will that be? Let's do that. 1 minus 1 minus 1 1 2 2 minus 2 minus 2. This is your mean subtracted one. Now what is the formula for your covariance? Your covariance is basically expectation of x minus x bar transpose x minus. This is the formula for general formula for your covariance matrix. Or maybe I should not write it like this. So for each sample if you take, so this is the formula. Now if you want to compute the covariance matrix here, so first let's take this example. So this sample point, for this you have you have 1 minus 1 transpose 1 minus 1, or maybe we can write it like one minus 1 1 minus 1. This is the first, from the first sample this is the value. Now plus from the next sample you will get minus 1 1 minus 1 1, plus you have 2 2 2 2, plus you have minus 2 minus 2 minus 2 minus 2, and you have to take the expectation of this. So when you have some finite number of examples, this simply reduces to population mean. So you just take 1 by 4 of this thing. So what will that be? Let's compute that. 1 minus 1 minus 1 1, first one, plus 1 minus 1 minus 1 1, plus 4 4 4 4, plus 4 4 4 4. So I'll write it here for now. That will be equal to 1 by 4
Ma'am, last matrix consider 4 minus 4 minus 4 4.
4.
No, it's minus to minus. Sorry.
Yeah.
I got it.
Yeah. So this is kind of the covariance matrix that you have for this particular data set. Now we have to compute the eigenvalues and eigenvectors of this covariance matrix to get the principal components. So our covariance matrix is this. So our sigma is 1 by 4, 10, 6, 16. Now you have to compute the eigenvalue for this. That is, you will, let's say lambda I am taking. This will make 0. So will become So can any of you compute this and tell me the values of lambda?
$16 and 4.
Okay, let's check. So if you just put through the formula minus b plus minus root over it will be b square minus 4ac by 2. So that will become, let me check, 16 and 4, these are the two eigenvalues. Now we will have to compute the corresponding eigenvectors. So these two eigenvectors will correspond to the two principal components. So first let us find the eigenvector correspond to, let's say, lambda 1 equal to 16. So how do we do that? That equation is, let's say our eigenvector is v1, then sigma 1 v1 is equal to lambda 1 v1. Let's say I am writing it as AB, it will be 16 AB. So that becomes So what will be the values for this? Is it something like this, or I'm making some error in this? Can anyone help me with the solution for this?
Ma'am, how we get 36b square is equal to 54 square?
Maybe I have made some mistake. Let me do it once more.
Yes.
Up to this point it is correct, right?
Yes, ma'am.
Yes.
Yeah, so now we have, if we just take the top equation, we get 54a equals to 6b, right? From the second equation we are getting so we can write sorry, b equals to 9a,
A is equal to B by 9, madam.
yeah, a is equal to b by 9, that's 9. So if we put it over here, 6 into b by 9. Okay, so I did the, yeah, I did some mistake over there. So this is again 9. So some issue is there. I'm making some mistake in the calculation. Just Is anyone able to solve this and can tell me where I am doing it wrong? Let's check the formula. So what is the formula according to you? Neelam, can you please tell the formula for calculating eigenvectors that you are saying?
Ma'am, we are getting A is equal to 9B. So we can say that A is 1 and B is 9.
A is equal to 9B, where we are getting that?
When we are solving the second equation, 6A plus 10B, which is equal to 64B.
Huh.
So there we'll get 6A, which is equal to 54B, which is means A is equal to 9B.
Yeah, but no.
So if we are considering that particular equation, so based on that we can find it out the value of A and B.
Yeah, but no, that answer is not correct. Okay, maybe I'll check this and I'll get back to you in the next session that what should be the answer for this. Actually, the answer for this, as far as I have the sheet, it's 1 by root 2 1 by root 2, and for the value 4 it will be 1 by root 2 minus 1 by root 2. So I'll write it.
Okay.
Maybe I'll get back to you with the calculation once.
Yes.
And you people can also try out the values. So for this it will be 1 by root 2 1 by root 2, and for this it will be 1 by root 2 minus 1 by root 2. Yeah, so this should be the final values. So let's assume that it is the value. We will go through the calculation once more in the next week. I'll definitely do this one. But if that is the case, then the question was so the question was choose the options below which one the PC algorithm would choose if you request just one principal component. So if you want to have just one principal component, we will take that vector which is corresponding to the highest eigenvalue. In this case this is 16. So you will basically choose this vector as your required principal component. So this is basically the vector that will be the principal component if you want to project this data to 1D using the PC algorithm. But this, yeah, there is some issue with my calculation. I'll get back to you. These eigenvalues are correct. This should be 16 and 4 itself, but the eigenvectors I have to look once more. I'll get back to you. But the process of computing PCA is clear to everyone, right? If you have any doubts, you can ask. If not, then let us move on to the next problem. So this is also on PCA. So which of the following two vectors can form the first two principal components? So 4 sets of vectors are given. So, you have to say which two among these can be the first two principal components of some data set. Can anyone answer this question? Anyone?
Option 1 is one component, madam.
It has both, right? Option 1 is the correct answer. Yeah, that is perfectly correct. These are the two the first two principal components. So, I will just explain if anyone has any doubt. So, all your principal components are supposed to be orthogonal to each other, because you are taking the eigenvectors in the eigenspace. These eigenvectors are orthogonal to each other. So, your principal components will also be orthogonal to each other. So, when you are given this set of vectors, you just have to check which two are orthogonal to each other, then you can say that those two are principal components. So, in order to do orthogonal, you can just take the dot product, and you have to if you get the dot product is 0, then simply that one is the orthogonal set. So, if we take the option 1, so our dot product will be 3 into 2 6 plus 3 into 1 3 minus 9. This is basically 0. But if you take the second one, that is minus 4 plus 4 minus 8. So, this is not equal to 0. These two vectors are not orthogonal. Third one is minus 6 plus 3 minus 9. This is also not 0. Last one is 6 plus 3 plus 9. This is also not 0. Only the first pair are orthogonal to each other. So, that can be the two principal components. Similarly, the next question, let us say vectors A and B form the first two principal components after applying PCA. A, it is given as 2 4, B is 3 1. B is n1, sorry. A is 2 4, B is n1, and these two are the first two principal components after applying PCA. So, under such circumstance, which among the following can be a possible value of n? So, again the logic is same. We have to make these two vectors orthogonal to each other. If that is the case, that is A transpose B will be 0. So, 2n plus 4 will be 0, that is 2n is minus 4 or n is minus 2. So, minus 2 is the correct answer. In order for Neelam, you are correct. Option B is the correct answer. For these two vectors to be the first two principal components obtained using PCA, n has to be equal to minus 2. Now, we have a very simple short question. So, let us say this plot, this x1, x2, these let us say that you have a set of 2D data points which lie on the locus of this curve shown on the figure. So, the question is, which of the following could be the direction of projection using PCA if the data points lie on the locus of the curve? So, along this locus your data points are there. So, what will be the direction of projection using PCA, that is the direction corresponding to the first principal component. So, any guesses for this one?
Ma'am, option C.
Yeah, correct. Option C is the correct answer. So, basically if your data points are in this kind of a locus arrangement, so if you compute the eigenvalue of the covariance matrix, the eigenvalue corresponding to the highest eigenvector will be along this, and the eigenvector corresponding to the other eigenvalue will be along this, these two will be. So, this is basically the direction of maximum variance, along that will be the first eigenvector. So, that will be the direction of your first principal component. So, it is basically making an angle of 45 degree with x axis in the anticlockwise direction. So, this is the correct answer. Now, let us see this one. Show that while projecting feature vectors to 1D space, PCA selects that projection direction along which the projected data has maximum variance. So, you are using PCA to project your data to 1D space. So, you have to show that the projection direction along which the projected data has maximum variance, that direction is selected by PCA. So, let us say we have our data set x1, x2 to xn. This is our data set that we have. We are using PCA to project these data to the 1D space. Let us say the direction along which the projected data has maximum variance, that direction be E. So, this is the unit vector, let us say, along this direction along which the projected data has maximum variance. So, this is your original data, and if E is the projection direction, then your projected data, let us say we denote those by yi, will be E transpose xi for I equals to 1 to n. These are your projected data points. So, now you want to have this, you want a maximum variance for this projected data. So, you have to compute the variance of this projected data. Variance is basically expectation of yi minus, let us say, mu tilde square, where mu tilde is basically the expectation of yi. So, this is the formula for variance of yi. Now, this means your yi here we have written it is E transpose xi. Now, E is a constant direction for all. So, you can simply take E transpose out and expectation of xi. Let us assume that the expectation for this is mu. So, your mu tilde is basically your E transpose mu. So, the mean of all the projected data yi is basically E transpose into the mean of the original data points xi. So, if we use that formula, if you use that expression in the variance, your variance is expectation of yi minus mu tilde whole square, and now your yi is E transpose xi minus this is your E transpose mu whole square. So, that is equal to expectation of, if you take E transpose xi minus mu into xi minus mu transpose E. Okay. E transpose and E can go out. So, expectation of xi minus mu into xi minus mu transpose E. So, this is basically the expression of covariance matrix of your original data set X, right. Let us say we denote that by sigma. So, this basically is the variance. So, this is the variance of the projected data. So, you want to choose such an E so that this variance is maximized. Now, these E again, these are the unit vectors. So, E transpose E is basically 1. So, our optimization problem becomes, we have to choose a vector E so that we can maximize this variance or we can minimize the negative of it, subject to the constraint that this E is the unit vector or E transpose E equal to 1. So, we can add that as a Lagrange multiplier. So, this is our objective function. We have to minimize this expression to get our E. J E is minus of E transpose sigma E plus lambda times. So, if you take the derivative with respect to E, it becomes minus 2 E plus 2 lambda E. This is the derivative. So, if you want to maximize this function with respect to E, you will have to make this derivative equals to 0, which leads to sigma E equals to lambda E, which is basically the eigenvalue equation for the covariance matrix. So, this here E is basically the eigenvectors of the covariance matrix and lambda is the eigenvalue. So, you see that your E basically satisfies this eigenvector equation for the covariance matrix. So, this E is basically the one having, we have assumed that this is the one having the that particular direction along which the data is having maximum variance. So, you want to maximize. So, you see that this E is basically satisfying that eigenvector equation, which is same for PCA, that also comes from that eigenvector equation. So, this E will be one of the principal components. Now, if this is the expression, your variance expression was E transpose sigma E, you can just put the value over here and you get lambda. So, your variance will be maximum for the maximum lambda. So, this is the variance of the projected data, that will be maximum variance will be equal to the maximum value of lambda. Now, if you put maximum value of lambda here, so the E is basically the eigenvector corresponding to that. So, you can see that is the same for PCA. So, basically in PCA the first principal component that you get, that is basically the direction along which the projected data has maximum variance. So, if anyone has any questions over here, you can ask, otherwise I will proceed to the last two problems for today. So, let us move on to this problem. This is a MCQ question. Which of the following is false about PCA and autoencoders? First option is both PCA and autoencoders can be used for dimensionality reduction. Second is PCA works well with nonlinear data, but autoencoders are best suited for linear data. Third is output of both PCA and autoencoders is lossy, and none of the above. So, what do we think is the answer which is false about PCA and autoencoders?
Option B, madam.
Yeah, correct. Option B is the correct answer. So, PCA is basically a linear transformation because we are just projecting along a vector along the projection direction, that is just a linear combination that we are performing. So, that is basically works well with linear data. But in autoencoders we can have multiple layers with non-linearities in the neurons. So, non-linear data can be well handled with autoencoders. So, this is basically the false option, but both of them are used for dimensionality reduction, and when we are doing dimensionality reduction, of course, the outputs becomes lossy because we are removing some in case of PCA we remove the principal components corresponding to the lower eigenvalues. So, we cannot completely reconstruct back. So, the output is lossy. In case of autoencoders also, that is the same thing. Now, the last question, this is on autoencoders. So, let us say a single hidden and no bias autoencoder has 10 input neurons and 10 hidden neurons. What will be the number of parameters associated with this network? So, your input layer has 100 input neurons, your hidden layer has 10 hidden neurons. So, can anyone tell what will be the number of neurons in the output layer, given this is an autoencoder?
100.
Yes, correct. So, in autoencoder we are basically reconstructing the input data. So, since our input data is 100 dimensional, we have 100 input neurons. So, our input data is 100 dimensional. So, of course, the data that we need to reconstruct should also be 100 dimensional. So, our output layer should also have 100 neurons. So, our network architecture is basically input layer with 100 neurons, hidden layer with 10 and output with 100. So, your hidden layer you can see has much less number of neurons as compared to the input and output. So, this will be the compressed representation that we will take. So, that is much lower in dimension as compared to your original data. But now, if this is the network and there is no bias involved in this, then what will be the number of parameters associated with this autoencoder? So, basically the weight matrix between this, that will have 100 into 10 number of elements. So, each of these 100 input will be associated with some weight to be connected to each of the hidden neurons. Like that, it will be connected to all the 10 hidden neurons. So, total number of parameters is 100 into 10,000 here and again 1000 over here, because each 10 will be connected through 10 weights to each of the output neurons. Similarly, we will have 100. So, total if you consider, you have 2000 number of parameters in this autoencoder. So, these were the problems that I planned for today. Of course, I will get back to that eigenvalue computation, eigenvector computation again in the next class. I will give you the correct answer for that. But if anyone has any doubts, we can discuss that and then close today's session.
I mean, this last question, if we include the bias, what will be the answer?
Okay. So, if you include the bias, so in hidden layer, for each neuron you will have one bias term involved. So, each neuron basically performs W transpose X plus B. So, one bias term is involved for each neuron. So, here you will have plus 10 bias terms, and in the output layer you have 100 neurons. So, all of them again will have one bias term. So, here we will have again plus 100 number of parameters. So, this is the number of bias terms is basically equal to the number of neurons. The weight will be much larger. So, this is from bias, this is from bias. Is that clear?
Okay, ma'am. Thank you.
Any other doubts from anyone?
Ma'am, question 5 of assignment 6.
Okay.
Question 5 of assignment 6.
Can you tell that assignment solution, everything is done, is it?
Yes, answer as displayed.
Okay, okay. What's the question? Can you just briefly tell?
The derivative of the loss function with respect to the weights in a deep neural network can be computed as,
Okay.
and there are the 4 options.
Okay, let me just open this. Week 6, right?
Question assignment 6, question number 5.
derivative of the loss function with respect to the weights in a deep neural network can be computed as sum of derivative of cost function, derivative of nonlinear. Okay, what's the doubt here?
Answer is option C, but I'm not getting.
Okay, so so the question is, you have to compute the derivative of the loss function with respect to the weight. So let's, if you just take a single let's say you just have a single neuron, you are giving some input and you are getting some output for this. Let's say your input is x and you are getting some output y out of this. So basically what this neuron does, a standard neuron, for this y will be some wx plus b it will do, and it will put some non-linearity, let's say sigmoid, on top of that to get your output value. Now you will have some target value for this output, right? Let's say that is t. So your loss basically is your some function of y and t, that can be mean squared error, that can be mean absolute error, cross entropy, something, some function of y and t, that is your loss, and this y is computed like this. Now you have to, let's say I denote this as L, you have to take the derivative of L with respect to W, right? So this is not directly related. So W is basically related to y, y is related to this function f, which is the loss. This f is basically the same. So you can, if you want to take the derivative, that simply becomes, first you have to take the derivative of loss with respect to your output, then your output with respect to your input. But here also one non-linearity is involved in between, right? So you can't, your x is not directly connected to y, it has to first go through the sigmoid. So you can write this as y, first you have to take the let's say if we consider this thing as let's say z, then it will be your del y del z into del z del x, sorry not del x, del w, right? Do you agree with this?
Yes, ma'am.
Yeah. So now this first thing, this is basically the derivative of your loss function.
Yes.
The second one is basically the derivative due
Non-linear.
to the nonlinear transfer function, and
Yes.
this last one is because of this linear network. So you are
Yes.
basically taking the product of these three to compute the loss function, because this is like concatenated operations are happening. First this linear, on top of that this non-linearity, on top of that some function to get the loss. That's why your derivative will also, chain rule will be followed to get the final derivative.
Yes, ma'am. Get it.
Mani is asking, explain regularization term in loss function. Okay, so Mani, regularization is basically so in order to make your network not overfit to some particular data set, we use different types of regularization techniques. Among that one is the adding some factor of some regularization term in the loss function. So for example, you have some loss function L, and so if you give your network the complete freedom of learning any complex function, it can learn such weights which is highly specific to the training data set. So many times we actually want our networks to be generalizable, right? Whatever we learn from the training data, you should be able to use that on a test data which is some unknown sort of data. So it's not only you have to learn the properties of this particular training data set, it has to be a generalized property of the data. So if you just use the loss function, it can sometimes overfit. So we try to put some constraint on the weights so that it is not that much overfitted. For example, we can try to have one constraint that your each weight value, the maybe the L2 norm of the weight, which is the Euclidean norm, that has to be below some threshold, that also we want to minimize, so that your weights are not very high weights that is particularly suited here. Or you can, let's say you can say that your weights has to be sparse, you want some of the weights to be 0, to not actually all of these are kind of trying to deal with overfitting, so that your weights are not that fitted to the training data. You are imposing some more constraint on this, so that you maintain a sort of generalizability on top of it. That can be L2 norm, L1 norm, or any other constraint that you put, that can be there as a factor. So you do not want your weight to be anything satisfying this L, it has to satisfy L, the loss, as well as its values should be some smaller values. You want to minimize the L2 norm also. So then in that case you use both of the factors with some coefficient of determining the contribution of the two. So you try to minimize both, loss has to be minimum as well as the weight values has to be minimum. Or you can have L1 norm, in that case you want the number of the absolute values has to be minimum. Or you can want that it has to be sparse, then some of the weights has to be zeros. Those kind of constraints are used as the regularization term, just to avoid overfitting in most of the cases. For example, other approaches are also there to avoid overfitting, like you can do early stopping of your model training. So when if you keep on training your model, if you keep on updating your weight, then after some time it can be that your training loss is reducing at each update, but if you test your data on some other validation set, there your loss is not decreasing anymore. So it has started to overfit to your training data, but you do not want that. So you can have a clause that I'll update as long as the validation loss is reducing. Once that stops, I'll stop. That is also one type of regularization, so we call that early stopping. But we can use regularization terms as well in the loss function to implement some sort of generalizability in the network. Yeah. Any other doubts from you?
Madam, what would be the problems for the next week? On which topic, madam?
Next week,
It would be better that if we take on convolution, CNN is been started.
just let me check. Yeah, we'll talk a bit more about autoencoders and we'll move on to convolution. Yeah, that will be the plan for next week.
Oh, okay.
Okay, so if no other doubts from anyone, then we can close the session today. We'll meet again on next Saturday. We will solve the remaining that unresolved problem. Okay, in problem 5, in problem 5, for finding covariance matrix we must not take 1 by 4 and then the, is it? But okay, Neelam is saying in problem 5 for finding covariance matrix we should not take the 1 by 4 and then take the eigenvectors can be calculated. But Neelam, that is the formula for covariance matrix. If we do not take the 1 by 4, that should not be the covariance matrix. I'll just check and get back to you on this problem, because covariance matrix is supposed to be the average of the expectation of those things. Okay, so if no other doubts are there, then I'll close this session today. We'll meet again in next Saturday. I'll definitely resolve this eigenvalue issue and we'll move on with other problems on autoencoder and convolution. Okay, thank you everyone for joining.